Hypothalamus, artificial intelligence. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents its solutions for decision-making, artificial intelligence, and disaster and emergency management. Part 1. Events due to nature. Framework. The challenge. Develop a DSS for disaster and emergency management. The overall objective is to minimize potential negative economic impact and human life losses. The solution. Design a set of mathematical models to address the problems arising from disaster management based on stochastic programming models. The benefit. A set of measures and mathematical models to prevent and/or reduce the impact of disasters, and it prepares the community to respond in the best way when a disaster strikes. The general approach of HI is to connect predictive and prescriptive analytics models, which implies an integrated holistic vision, multidimensional space-time, of the entire supply chain of disaster response services. Predictive analytics is based, mainly, in artificial intelligence, machine learning, and complex probabilistic methods. Prescriptive analytics in mathematical programming, better known as optimization. Activities to ensure safety. These mission areas may be grouped based on when a defensive action is intended to occur, either before, during, or after an attack. Proactive planning. Mission areas whose defensive actions are taken before an attack occurs. These mission areas are prevention/protection and mitigation. Real-time operational planning. Mission areas whose required actions are taken during or immediately after an attack. These mission areas are detection and response. Recovery planning. Mission areas whose required actions occur after an attack. This mission area is recovery. Natural disaster management. The mitigation and preparation of disasters caused by nature implies. The overall objective is to minimize the potential economic and human loss, and continuity of operation of the economic system. To this end, the historical behavior of nature is studied, trying to know probabilistically what can happen in order to make decisions of where, when, and how to allocate resources to mitigate and/or prepare for the disaster. Actions before mitigation, set of measures to prevent or reduce the impact of disasters. Preparedness, preparing the community to best respond when disaster strikes. Given the uncertainty regarding disasters, the theory indicates that the only way to prepare for disaster is to probabilistically characterize risk, with predictive analytics, and based on that information to make optimal decisions on how to mitigate it, and how to prepare for it, using prescriptive analytics. The process involves making decisions in advance, regardless of any future scenarios, and simulating decisions for each of those scenarios. The decision should consider the expected value of the benefit, or the cost, and the control of extreme risks, which should not be assumed. The process of stochastic optimization involves 3 stages, 2 of predictive analytics. Stochastic process model converts historical data into a dynamic probabilistic model, and synthetic scenario generation turns the dynamic model into a synthetic scenario tree. When there is enough data, these 2 processes can be algorithmic, otherwise it is necessary to resort to a committee of experts. And 1 stage of prescriptive analytics. Stochastic optimization, it converts the scenario tree to here and now decisions, and with the simulated future decisions generates probabilistic distribution functions for the future. The model should include extreme risk control constraints. It is suggested to use the conditional value at risk as a risk indicator. In this case, the decisions to be implemented are associated with the optimal resource allocation policy for mitigation and preparation. Actions after reaction, the use of resources and emergency procedures to preserve the life, property, and environment of the community, since the disaster is occurring. Recovery, set of long-term actions to stabilize the community and return to normalcy. The reaction and recovery after the disaster occurs implies actions during the disaster, and reconstruction actions. Earthquake Management in Seattle. Pacific Rim Visualization and Analytics Center, PARVAC. It is made up of the following computer components. GOSR, Geospatial optimization of strategic information and resources. Platform of mathematical models and numerical algorithms for decision support in emergency management. JIC3, Just-in-Time Mobile Command and Control Environment. Command post for the deployment of personnel in emergency response, to optimize the flow of information about the emergency and response during an emergent event. RIMSIM, First Response Simulator for Common Pacific Rim Threats. Software based on a modular system, to simulate first response communications, common artifacts, and response actions in order to evaluate and improve the level of distributed knowledge, and VisSearch, Visual Search Aid System, by means of image or pattern detection strategies and technological mediation. Decision support systems for disaster preparedness and response are challenging because uncertainty of events and difficulty obtaining real-time data. GOSR development optimization models for the location and allocation of medical supplies to be used in emergencies for the Seattle region. The distribution of supplies requires at least the decisions before the event, location of warehouses, and inventory levels of medical supplies after the disaster. Optimized allocation of medical supplies to hospitals to reduce delivery time. In the preparation stage, RIMSIM and GOSR integrate personnel training into a disaster command center. RIMSIM is used for simulation of the training environment, on the other hand GOSR is used for optimal decision making. In the response stage, GOSR is used for real-time transportation decision making, while supply-demand information of the disaster is collected. The models to use previous to disaster are Stochastic Optimization Model, selective warehouses, and determine inventory levels by balancing disaster risk with on-time delivery of supplies. Transport Model, transforms transfer orders into optimal vehicle assignment and routing. In the response phase, the fundamental model is Real-Time Optimization Model. It results in the allocation and routing of vehicles with up-to-date information on transport conditions and current demand and supply information. In this academic example, 2 Seattle earthquake scenarios were considered for the analysis: Seattle fault, M6,7 with probability 0.6, and Cascadia fault, M9,0, with probability 0.4. Additionally, it was considered 3 warehouses, 10 hospitals with demands of health services depending on the fault, 62 routes that connect warehouses with the hospitals, and 1 type of medical supply. The table presents the results obtained for the preparation stage, including inventory levels in each warehouse, expected quantities transported between warehouses and hospitals, and routes used. Inventory levels are decisions variables here and now, and they are independent of failure. Transport flows depend on each scenario, they are simulated variables. Case: Earthquake management in Istanbul. Case: Rebuilding New Orleans. Case: Seismic risk management in Italian Tuscany. The document: Earthquake risk management via stochastic optimization, a case study for an Italian region. It describes how a stochastic spatial dynamic optimization model, which considers the complexities and interdependencies of catastrophic hazards, has been customized to explicitly incorporate the geological features of a region, the parameters of seismic hazards, and the vulnerability of the built environment. The model can analyze the interaction between investment and mitigation measures, and risk-sharing measures. Special attention is paid to the evaluation of a multi-pillar earthquake loss propagation program, involving the central government, and mandatory insurance. It is shown that the model can analyze multiple policy options, to develop insurance policy in an equitable and fair manner, and their effects on insurance premium and reserve funds. To analyze system stability, EASA uses a strong connection between non-differentiable stochastic optimization and risk measures such as value at risk and probability of insolvency. These data have been incorporated into a Monte Carlo generator of seismic events, which simulates the occurrence of earthquakes affecting the region, calculates the attenuation according to the geological characteristics, and finally determines the acceleration in the ground in each municipality. EASA's stochastic spatial dynamic optimization model has been customized to explicitly incorporate the vulnerability of the built environment, with data on the number and types of buildings in each municipality. In the first phase, the study has been limited to the study of different policy options for an insurance program. The next phase investigates the interaction between investments in physical mitigation, retroadaptation, and risk-sharing measures. Climate risk management. Case, sowing planning. One of the important risks, in which all companies are involved, is associated production processes in the bioindustrial sector, which are seriously affected by hydroclimatic conditions, whose volatility is increasing because of the global warming that is occurring on our planet. This situation means that the risks associated with the industries, whose financial statements depend largely on the climate, must be assessed and managed. The biggest problem for companies in the sector is that they must intervene in the process of sowing and harvesting bioindustrial products, since the management carried out by the operator derives the risk that a third company may end up assuming. Ignoring this situation can lead to a significant reduction in economic benefit for a private company or a state-owned enterprise. In addition, the high geospatial correlation of climate must be considered, which increases risks, and the concentration of risks in a region, or in a type of product, must be carefully considered. Public health systems optimization. Mathematical algorithms for epidemic management, based on high-complexity mathematical methodologies, will prevent the most deaths. Public health management implies challenge, to design and implement a DSS to pandemic management. Solution, design and implementation of a DSS aimed at pandemic management integrated by the following high-complexity models. Epidemic simulation model. It simulates the spread of the epidemic as a result of a mix of control policies to deal with the epidemic, mitigation, confinement, and vaccination. Modeling divides the territory into regions, the population into socioeconomic segments, and time in seasons, in order to have a dynamic epidemiological model including multi-infected states, multi-region mobility, and multi-socio-demographic segment. Epidemic management optimization model. It optimizes control policies, the use of health supply chain, HSC, resources, the optimal expansion of HSC vital components, bearing reference to the epidemic control policy optimization model, and the vaccination processes. Epidemic socioeconomics impact model. It determines the socioeconomic impact of pandemic control policies on the economy. Integrated with our S/OPT, it can produce dynamic pandemic control strategies that balance those contradictory objectives that may arise in the epidemic management process, minimize human deaths and maintain the economic's health. And epidemic state estimation model. Hybrid predictive analytics model, based on the distributed Kalman filter, to track the pandemic. Pandemic management optimization process implies research in the following areas: epidemic theory, smart sampling, identification of epidemic model parameters and the epidemic state, and mathematical programming optimization models oriented to control and management of the pandemic process. High health integrates with high RPO, regional planning optimization. This implies that all models of the two systems can be integrated through the database, common data model, or by means of equations that integrate a unique holistic model, this following the principles of structured mathematical modeling. This integration is since the management of public health problem corresponds to regional planning problem, as experienced during the COVID-19 pandemic. Anticipation. It is the core of decision-making under Environment 4.0. It is not a question of reconstructing the damage caused by a disaster, with decisions a posteriori. It is about anticipating and mitigating with actions before the disaster. And the best way to do that is to use the mathematical modeling power under the new technological paradigm. Like Carl Friedrich Gauss, hypothalamus artificial intelligence believes that mathematics is the queen of the sciences. Thank you for your attention.